Good morning, everyone. Can you all hear me?
Yeah, we can hear you.
Okay, good. Thank you. Did you see the lab manual and the video module? Has anyone
Yes.
seen? Okay.
I was just wondering though, because the first image kind of covers some of the writing.
The lab video?
No, for the lab like instructions, the paper.
Oh, okay.
Like here, I have it printed out. I can show you.
Yeah,
Here, like covers it.
I'll upload the PDF copy because mine is not like that. I think because it's Word document, it's was it Word document?
I think so, yeah.
When you open on a different laptop with different version of Word, it kind of rearranges everything. Mine is still okay. The image is where it's supposed to be.
Okay. And I was wondering, I don't know if this is just like what we're supposed to fill out or figure out, but I just wanted to clarify, just check. Because it says like, oh, which can be rewritten, and then it shows like equation 1, but there's no equation there.
Okay. Does anyone else have that kind of issue? Mine is showing the equation 1. Is any other person having that kind of trouble viewing the document?
No, the document for me is fine.
Okay. So what I'll do is I'll try to immediately after the class, upload a PDF version.
Okay.
Okay.
Thanks.
You're welcome. Okay, so today we are looking at the second part of our chapter 11. And by Friday, we should be done with chapter 11. Then next week, we'll be done with chapter 12. Chapter 13, which will be the last week of our lectures. We'll only have it twice because lectures will be ending on the 8th of December. All right. Okay. So today we're starting with the first law of thermodynamics. I'm sure we are familiar with this, but just a kind of reminder what the first law of thermodynamics is. So whenever we talk about thermodynamics, we're also talking about, we talk about the analysis or understanding of energy of a system, be it isolated or open system or closed, okay? So, but we have also discussed something earlier that was recurring in our problem solving patterns, and we call that the work energy equation. We know that the work energy equation simply tells us about change in energy being equal to work done for a system that has interaction with its environment. But for a system that is isolated, no work is done. The internal energy is constant. That means change in energy is equal to 0. So that understanding is what we modify to understand some systems that don't work exactly how or like an ordinary phenomena, all right? And that is what informed the first law of thermodynamics. And the first law of thermodynamics simply included or factored in the important point that heat is also part of energy changes that go on in the system. So we see that this simple equation that appears to look like the work energy equation without the Q. Without the Q, it's a work energy equation, but with the Q now, it's modified work energy equation. And this is the expression for the first law of thermodynamics. Okay, we will define the first law later in the class, but just to tell us where that definition is coming from. That is why we're explaining this, explaining the total internal energy of the system being equal to the work done plus heat. We have looked at heat before in our previous class, and we know the signs. When the system is gaining, the heat sign is positive. When it's losing, it is negative. Okay, so we see also that heat and work, they are the factor or parameters that the system interacts with the environment, right? You remember that two arrows bringing in heat and work to the system. So thermodynamics is actually studying the system's interaction with its environment, okay? So if we consider a system that only the thermal energy in that system is changing, the system is not moving, and there's no change chemically, but its temperature is the only change that we can recognize. Such a system with change or dynamic temperature is what we call, or we use to describe thermodynamics, from the word thermo and dynamics, which is like constant change in a system, all right? So that's the origin of the word thermodynamics. So thermodynamics works in such province where there is purely thermal energy change in that system. So we'll be looking at the thermal energy change and heat, and also we'll look at the relationship with such system and other forms of energy as they transform. So this whole part is basically what thermodynamics covers, both the first and the second law, okay? So we should also keep in mind that we'll look at the application of this law to our natural phenomena, okay? And it is this law that we use to, wherever you see where temperature is controlled in terms of cooling and heating, it is the law of thermodynamics that comes into play. So we'll begin by looking at the first law. What is the first law of thermodynamics? So for a system in which only the thermal energy changes, the change in thermal energy is equal to the energy transferred into or out of the system as work and heat, or both work and heat. So once you remember this equation or the first expression, you should be able to define the first law of thermodynamics. Remember, we said that in the first case where we're looking at energy and how it interacts with the environment, these are the two factors, heat and work, okay? So we'll see a typical system that is interacting with its environment. We see it's exchanging heat and work with the environment. When the system itself is gaining, we say it's positive. So work is greater than 0, heat is greater than 0. They both go into the system. So they're bringing in energy into the system. And then when they are giving out to the environment, as indicated with this arrow, we see that it is taken away from the system. So work is less than 0 and heat is less than 0. So energy is being given out, okay? This is purely what happens with a thermodynamic system and its environment, be it a cooling process or a heating process. It's simply the control of intake of energy in form of heat, then work, and giving out as well. Okay, so if you're asked to say something about thermodynamic or a short note or a definition, you should be able to say it in words and also represent it with equation. Okay, and when you do that, make sure you define out the parameters. We didn't have to define the parameters one after the other here because we already have the definition of these parameters. You know what this is, thermal energy, you know what this is, the work, and you know what that is, the heat. Okay. So let's see an example to drive home the point about the first law. Okay. So keep in mind the first law is saying it is the change in energy being equal to both work and heat exchange of the system with the environment. Okay, so once the system is kind of specified, once you specify the particular kind of system, you'll be able to manipulate the data where work can be 0 and when heat can be 0 and all that. Okay, so let's see an example. If you put an item in the blender and you blend, you discover that the item you put in the blender kind of gets warmer or heat up. So when you feel the temperature, you feel that, okay, the temperature of this object increased. What exactly is happening? Okay, so we see a level of a thermal exchange happening there. So suppose the blender motor runs at a power of 250 watts for 40 seconds. During this time, 2,000 joules of heat flows from the now warmer food to its cooling environment, as cooling surrounding. There's an exchange. By how much, this is the parameter you're looking for, by how much does the thermal energy of that food increase? Okay, so picture what is going on. You put an item in the blender, you heat it up, the food that is now warmer is now exchanging heat or exchanging thermal energy with its surrounding. By how much? The question is, by how much does the energy of that food, thermal energy of that food increase? Okay, so we'll go from the parameters given, they specify the power, work done. Remember where we derive this equation? Work done from power equal to F, the rate of energy change. Remember power. We define power in 3 ways. It is FV, rate of energy change. We have 3 definitions of power. So we just deployed one of it to typify what is going on here, which is the rate of work done. When we made work done the subject of formula, we now have power being equal to, work done being equal to the product of power and the time taken. So, and these 2 parameters are given to us here, the power in watts that the blender is operating with, and the time length of operation, which gave us the work done of 10,000 joules. Okay, so if the work done is given, W, we know our heat that was giving us 2,000 joules of heat. Now they put the statement which brought in the negative sign. Remember we said when the system is gaining, it's positive. When it's giving out, it's negative. So the system, which is the now warmed food, is the one interacting with the cooler environment, so it's giving out. And hence that 2,000 is negative. Okay, so you cannot just plug in the data. You have to also pay attention to the information that is supplied in the question. So with that information, we just impute into the first law of thermodynamics to calculate the thermal energy. Remember, first law or thermodynamics is just going to be concerned with thermal energy. And that is why we said, consider a system whose thermal energy is changing and every other thing is just the way they are. So putting that in, we'll have work and heat. That's work plus heat. Because this is negative, that is why this became minus. We'll have the thermal energy of 8,000 joules. You see that it's pretty straightforward and easy to grasp. All right, so that is just the summary of what the first law of thermodynamics entails. It's far bigger than that, but for now, that is the little we should take home with from that first law. So let's look at what we mean by the energy transfer diagram. We have seen that thermodynamics is going to be concerned with the energy exchange, and also it's going to be concerned with the kind of transformation that goes on with the system and its environment. So to better understand that, we have to look at also the energy transfer system. Naturally, when there's energy transfer in terms of thermal energy, it's going to flow from a more heated part to the cooler part. Okay, so we have how heat, which is QH, will stand for the heat for when it's hot, and QC will stand for the heat when it's cold. Okay, so we see the heat energy transfer from hot to cold. This rod is being heated up. The hot part, which we call the hot reservoir, will have the temperature TH, H meaning hot, and also C meaning cold here. So it's moving from hot to cold region, which is basically the movement or natural movement of heat. All right, so this is just the definition of what we mean by QH, the amount of heat transferred to or from a hot reservoir. You can be going into, but QH means hot reservoir heat, and QC means cold reservoir heat. Okay, so we already know that what the definition of the science of heat, but by definition in this case, QH and QC remains positive. They are positive quantities. All right, so we'll look at also the scenario in B, where the heat energy is transferred from the hot reservoir with a connecting pipe. You see the connecting tube serving as a system of exchange, moving down to the cold part. Now this movement exchange between the hot and the cold brings about a balance, because it will keep exchanging heat with each other until the two of them will have the same temperature. There will not be need for any further exchange. So we see that the total energy of that system also will be conserved, and the heat will be conserved. And to reach this conservation point, the heat for the cold has to be equal to that of the hot. Okay, so when QC is equal to QH, we say the energy of that system is conserved. All right. The same vein, this is the hot reservoir, and this is the cold reservoir. And this is the copper bar that is serving as the system marked out with the red sign there. Now, what we want to buttress here in the energy transfer diagram is that the natural process of heat flow will go from the hot reservoir to the cold reservoir. Now, this heat flow process can actually be manipulated, which we will look at shortly in the next 2 slides. Okay. So if you have an energy reservoir, when we use the word energy reservoir, we're talking about either the hot or cold reservoir, their energy reservoir. Okay. An energy reservoir is actually, when we use the word, an energy reservoir, an object or part of the environment that is so large enough such that its temperature does not change easily. The change is not or does not noticeably change. Okay, so you have an object that can absorb temperature. Such an object is called an energy reservoir, just like your batteries. And we'll have other natural phenomena like the ocean. No matter how you try to heat up the ocean, it's going to take a lot. Let me not limit science saying that they cannot heat up the ocean. There may be a scientific discovery tomorrow or a process that can heat up an ocean. But it simply buttresses the point that a reservoir will be able to take in large temperature without a noticeable change. Okay, so when heat is transferred between the system and the reservoir kind of serves as a buffer to what that system is. And that's why we use the word reservoir. It's storing up. You can take from it, you can put into it. So a reservoir at a higher temperature than a system is the one we call the hot reservoir. And the reverse is also the cold reservoir. Okay, so we have an example of the cold reservoir like that of the ocean. Now we use the temperature TH and T2, which we have seen before, to designate the temperature of the hot and the cold reservoir. And we use the QH, QC for cold and hot. So we'll move on to the next thing we want to look at today, which is the heat engine. Now, the heat engine science actually deployed the understanding of the natural flow system in the first law of thermodynamics to manipulate materials such that it can make them go the reverse to nature. Okay, so I mentioned earlier that we'll be looking at how this natural flow can actually be manipulated to our advantage. All right, so the heat engines were the first set of application for this kind of science, manipulating the natural flow of the heat system or thermal energy system to yield the benefits or human or benefits in technology. So a device known as heat engine takes some energy, and as it's being converted into other form, takes such energy to do work. Okay, so the heat engine takes some of its energy as it is transferred or converted to other form. Such system is what we call the heat engine. Okay, so let's see quickly the picture or that represents or typify a heat energy system. So let's look at the image A. The heat energy, QH, when we put the QH, you mean the hot reservoir part of it, okay? It's already stated here as well. You see the system, the hot reservoir part, exchanging energy or exchanging heat with the cold one on a natural flow, going from hot to cold. And as that process is going on, it's taken from the heat exchange or transformation to do work. Okay, so part of that energy is used to do what we call useful work done. Okay, so we have engines that are able to divert or manipulate this natural process to achieve an aim. So let's now put a name to what you're talking about. Look at this turbine or power generator. This is driven with the steam coming up from the hot reservoir. So you have water here that are heated up at high temperature. The steam moves up, turns this rotor or turbine to bring about useful work done. Okay, it can be used to generate power, it can be used to run a machine for whatever purpose it's designed for. But the process is that we have machines or engines that we can use heat to drive to produce a work output or useful work done. So we also see that in the process of heating this, we have the cooling or cold reservoir as well, like the river, it can be a drum. Some engines have artificial reservoirs created to bring about the continuous flow. As it's going, the steam goes back, cool down, back into the system, heats up, and goes on like that. Okay, so we have such engines that are functioning this way using the steam or process of heating up and cooling are called the heat engine. Okay, so there's something about the heat engine that is worthy of note. The heat engine, and that is the diagram here, cannot have 100% output. Let's say heat is going this way, and then you divert it totally to produce work. No, some will also have to go to the environment or have an exchange with the cooler reservoir region. Okay, so this can never be a possibility. And that is why we have that there's no 100% useful work done that can be obtained from a heat engine. Okay, so that means that we can actually use the understanding of efficiency to explain the process of heat engine as regards to quantifying the work output, the work done. Okay, so the work done equation from the natural process is that the cold heat takes from the hot one to give us the value for our work done. So the energy input to the engine, which is the H, what you give in, and then the energy output, which will come also as form of work done. We'll subtract the cooling or the loss. It's not really a loss, but the one that goes to the cold reservoir from it to obtain that. So to compute the efficiency of the heat engine, we use the same equation of efficiency that we have used before. And it simply means what you put in or what you get, what you get out over what you put in. Okay, and that's expanded, from this first equation, work output or useful work done is equal to QH minus QC over what you put in. Okay, so this point is just telling us the point we have already explained here, that we are also using this understanding to derive another concept in thermodynamics that we call the second law, which we will see later. But the reason why we brought it in here is that we actually need it to define better the concept of efficiency, okay? And that brought us to what we call the theoretical maximum efficiency of an ideal heat engine, okay? And that we call the efficiency max. What is the maximum efficiency that any heat engine will operate on? No matter how you try to optimize it, it's not going to be more than this, okay? So the maximum efficiency is equal to 1 minus the temperature of the coal over that of the hot, okay? And remember this measure of temperature must, note the word must be in Kelvin. In our last class, we've seen temperature scales that can give us Fahrenheit, degrees Celsius, and how we can convert them to Kelvin. So if they give you any question in Kelvin, in Fahrenheit or degree, you have to take it to Kelvin first, then you apply to solving the problem. Okay, so for heat engine, we use the Kelvin scale to define our temperature. All right. So we are simply buttressing or emphasizing that the efficiency cannot exceed the efficiency mass. Okay, so let's take an example. Example 2 today. Iceland has both the geothermal activity, that's thermal exchange from the environment, this is what geothermal activity, with high temperature near the surface, the abundant cold surface water. Okay, so Iceland has many power plants. This is a story trying to explain the conditions of operation in Iceland, but let's go straight to the question. One plant uses an underground source at, look at the value, is given to us in degrees Celsius. So you keep that in mind, must be in Kelvin, okay? So one plant uses an underground source at 122 degrees Celsius as the hot reservoir, and a nearby lake that is 5 degrees Celsius as the cold reservoir. That's the operation of the plant. The hot reservoir source, that's the temperature, and the cold reservoir is the lake, which is one of the examples we saw. It can be an ocean or a bath of cold water. So the plant draws 16 megawatts from the hot reservoir to produce 1.8 megawatt of electricity. How does the actual efficiency of this plant compare to the theoretical maximum efficiency? Is this plant operating at its maximum, or it can actually be optimized? That is the implication of what they're asking from us. Okay, so to begin, we put out the equation of efficiency here. Okay, that's here. So the work output is clearly stated, and the input, it draws, and this is what it gives. So what you get, what you pay. So we have the efficiency of 0.1. Now, the question is the theoretical maximum efficiency. So we want the maximum possible efficiency of that plant. How can we calculate that? So we apply the equation for maximum possible efficiency, and we converted this value to Kelvin. How did we convert it? Kelvin to Celsius conversion is pretty straightforward. It's by addition or subtraction of 273. Okay, so, but in this case we added because it's going from degrees to Celsius to Kelvin. So we did our conversion first. We now have our values in Kelvin, then we can now impute into this equation. When we did that, our final answer became 0.3. Now we see when we compare, because the question is actually asking you to compare. So after answering this kind of question, you have to make a statement that shows that you have done a comparison. From the value, the maximum efficiency is higher than the already operating efficiency. So the machine is operating not at its maximum. We can also go further to say, okay, this machine is operating at so fraction less than the maximum efficiency. And what I mean by so fraction is you can simply get the difference between these two and you quote that value. And if you do that, it will be maybe 0.0 something or 0.9 or 1 point. When you get the difference between these two, you quote it to answer the other part. Because if it's an exam, there'll be a score for that statement, and then there'll be a score also for showing your expression. All right? Okay. So we'll move on to the very last part of today's discussion, which is the heat pumps. Now, one way to always remember heat pumps is that we use this, it's not a scientific quote, but we just say the river that flows uphill. Now, what do we mean? River is supposed to flow downhill, right? But you just say river that flow or water that flow uphill. Because that's the first idea when this discovery came up. It's this person discovered a system that he can actually manipulate a natural process to go in the reverse. Yes, we have seen the heat engine, which applied the natural process. But how do we advance this? The heat pump is like an advancement in the control of thermal changes to technology. Okay. Now, the reason why I said river that flow up is that is emphasizing the point that it is a phenomenon that is made to go the reverse to nature. All right. So heat pump transfers energy from cold reservoir to hot reservoir. You see, the heat pump is able to make that natural system to go in its reverse natural form or reverse to its natural form. And it can also do the vice versa. So the heat pump can actually be adjusted or manipulated to do the taking off and putting in. And this is what we applied in many of our devices that are of help today. One of which is the water dispenser. We'll have the refrigerator, and we'll have the air conditioner. We'll have systems that you can actually control its temperature to go either the warm or cold way. Okay. So such systems are referred to as heat pump. All right. So let's see this example of this dispenser. We see inside the chamber, we have the QH, which is the hot reservoir, and we'll have the cold part. Then the electric energy brings in a useful work done. Okay. When we're talking about heat engine, we're talking about work out. It's more of diverting that natural process to produce work. But in this case, we're using another energy to produce our desired outcome. Okay. So a reversible heat pump is that type that can do both ways. It can make cool and make hot. And that's what you see in the application of your air conditioner. You can actually heat up your house or your car or make it cool. We use the kind of heat pump that is called the reverse heat pump. Okay. So, and that's advances to modify the equation a bit from what we used to have, although it is the first, because I said this is advancing the heat engine science. Okay, so energy must be conserved in any system. Energy is neither lost nor created, but it can only change form. So the heat deposited in the hot side must be equal to the heat or the total sum of the heat that is removed from the cold side. So when something is cold and you are removing heat from it, guess what? Cooler. When something is cold, you are adding heat from it. It's going to get warm, right? So that's just the basic principle of cooling and heating up. So, and that is harnessing also the interaction of such system with its environment. So let's quickly see the flow, the energy diagram of the heat pump. You look at the direction of the arrow, you see that it's going in reverse to what you've seen before. It's flowing uphill, okay? When the natural phenomena says downhill, it's flowing uphill. So that's the idea of the water that flows uphill that I said earlier. So you see the QC standing for this, and the temperature, the heat pump, taking the cold heat to the region of the hot heat. So the external work is used to remove heat from the cold heat reservoir and then send it to the hot bed. Now, the unique thing about the heat pump is that for us to talk about its maximal function, we're not using the word efficiency per se, but it is actually efficiency because it is also the equation of efficiency that we use. But instead of using the word or analogy quantity efficiency, we use this word called the coefficient of performance. All right. So the coefficient of performance for a process that is going from cold to hot and a process that is going from hot to cold is the same, but the equation will be kind of reversed, and we'll see the difference in the expression of the equation. But basically the equation is what you get over what you pay, which implies energy removed from the cold. So if it is a hot, it's going to be hot on the top, all right? So energy removed from the cold reservoir over the work required to perform that transfer. So we'll have the work in, the QC over the work in, that is work that is required or put into the system to perform that transfer, all right? So just like we had the efficiency maximum in the previous case, this case, we are going to be having the coefficient of performance maximum. And that is given by the expression TC over TH and minus TC. So this is the theoretical maximum coefficient of performance of the heat pump used, not the word, for cooling. If it's going to be for heating, the expression is going to take the same form, but in the reverse, all right, which we will see shortly. You see, this is QC telling you it's cooling, and this is H for when you're adding heat. And you see the theoretical expression also saying the outcome, which is the temperature for the heat side minus the cool. Temperature for the heat side is also minus the cool. So this is also the theoretical maximum coefficient for the heat pump when it is heating up. So we should keep this and this in mind. Okay, so we'll just take one example to buttress our point. So before we take that example, I just want us to note this, that the larger the value of the COP, which is coefficient of performance, it means the more efficient heat pump. It simply means the efficiency of the heat pump, but in this case, we're not using the word efficiency, we are quantifying the coefficient of performance. And efficiency is actually also the quantification of coefficient of performance of engines or machines. Okay, so it's just the terminology that is different, but they mean the same thing. All right, so let's look at the The last example, a heat pump moves heat from the chilly 8 degrees Celsius air outside a house to a toaster of 21 degrees Celsius air inside. Okay. The actual coefficient of performance is given to be 3.2. A, that is a typical value for the COP of most of this heat pump. Okay. When you get a heat pump, you will see this value, COP, then there's a value. Today, you know what it means. So the first question is, if the system adds 11 kilojoules to the house each second, how much electric energy is required? Okay. Remember our equation, work in, work out. But first you have to read the question, understand, is it heating up or is it cooling? Because that will determine how you will arrange your equation and the parameters given. The common mistake is to get the reverse, okay? So the second question is, how much energy will it take to add 11 kilojoules each second if the heat pump runs at the maximum theoretical efficiency? So we'll be looking at both to solving the problem. So the first thing we did is we remember the statement that said the temperature must always be in Kelvin. So we did the conversion. What we did is to add the 273 to convert this value to Kelvin. We did that also for this side.
Would it be the same for Fahrenheit?
No, the Fahrenheit expression has the, depending on which one you are converting to which, the 9/5 and the 5/9. Then you take to degree Celsius before you take to Kelvin.
Oh, okay, thanks.
Okay, so to solve this, we applied, this is just our energy equation, you know, I just picked it. But we are using, we can go back to see the equation we are using, which is C cup H in. We made this the subject of formula, COP equal to QH over WN, W in. If you make this the subject of formula, it becomes W in equal to the heat of the hot reservoir, COP. Okay, so that's the equation we used here. So applying that equation means the system is what? The heating up, referring to the hot reservoir because of the QH you can see there. So we'll put that value which was given to us to obtain the work that was the electrical energy required to do that every second. Is 3.4 kilojoules. Okay, now the second question says how much energy. We have defined the quantity of energy in the first case. And then the second one is saying how much energy if we make this machine to run at its maximum. So first we'll determine the maximum COP, that is coefficient of performance. So to determine that, we apply the maximum coefficient of performance expression for the heating system. If it's for cooling, you know this will change, okay? The arrangement, it's going to also have the temperatures for hot and cold, but their arrangement is going to be different. So obtain 23 as the COP for this machine to function at its maximum. It was currently functioning at 3.2. So it's the machine has not gone half its capacity. So that is when you hear people say this machine is operating below its capacity. It can actually be made to do more. So at its maximum capacity, the coefficient of performance is 23 for this heat pump. And then the required energy to operate this machine at its maximum will be 0.48 kilojoules. And what we did to make Q the subject of formula in the COP max equation for heating, we have the parameters supplied, 11 kilojoules, and the COP for max as determined to obtain this. Okay. So we have some practice questions for you here, just to lay your hands on. Now, somebody sent me a mail to ask what the exam will cover. The exam is going to be a comprehensive one, meaning it's going to cover from what we've done from chapter 1 to 13, all right? And I advise that the person should go through the text, check the examples, especially those ones I used to recommend you should look up to or study, and do the classwork, go through also the slides, some of the practice questions. We're not going beyond what we have defined to be the scope of the course or what we have interacted with, okay? So just to add that, to answer every other person that may have that question in mind and plan to send me an email. I hope I've been able to answer that now, right? So we'll meet in lab today for the very last physical lab. If you've missed any of the lab, please, when we get to the lab today, see me so that we can schedule the makeup. The makeup should happen next week. After next week, we're not going to have that again. And if you missed any of the tests or have any reason why you did not submit any of the assignments, most of us did not submit assignment 7 and 5, and which other one? 8. I have just like 18, some 12, like that. Please also see me so we resolve that. All right. Thank you so much. Does any of us have comment about today's class or question?
No, thank you. Yeah, I'll see you at lab, I guess.
Okay, it's all good. I'll be uploading the PDF copy. So if you have issues with the Word document, check the module again for the PDF and try to take out time to watch the video so that the lab will be easy for us, because it's an extract of our chapter 13, which we'll be doing the next 2 weeks. Okay? All right. Have a great day. Bye-bye.
Bye.